All right, guys. So it's time for fun with math here, and so we're going to kick it off here with integration by substitution, our first technique of integration. And so, what's the idea? The idea is how do we integrate something that looks like this? So first of all, you want to realize it's not one of our types. So we're going to have to do something to turn it into one of our types. So the idea of integration by substitution is to basically just let u be the thing on the inside. So that's kind of a general rule that usually works. And if that doesn't work, then we can be a little bit more fancy and look for a function and its derivative. So let's start with this idea of, looking for the thing on the inside. So when you see this integral here, hopefully you see that the inside would be this piece right here. So we would actually let u be equal to x squared minus 1. And if we make this what's called a substitution, then this integral will be transformed into one of our types. So let's just look at an example down here. The same one we were looking at before right here. And so I'm going to recopy this down so we have lots of room to work. So the integral of 2x, x squared minus 1 to the 10th dx. And so we're going to let our u be equal to the thing on the inside here. We're going to let it be equal to this x squared minus 1. And then we're going to take its derivative. So here we're going to write, all right, du dx for the derivative of u with respect to x, and I get 2x back. And normally I kind of skip this step because what we like to do is we like to write this little du or dx on the other side, like that. So then you can see very clearly the substitution. So right here, I'm going to replace this with u because that's what it's equal to right there. And then this 2x dx, I'm going to replace that with what it's equal to. So it's equal to this du piece over there. So it's going to be equal to the integral. And so I have u to the 10th. And then that 2x dx becomes just du. And sometimes students will ask me, hey, hold on a sec, where'd all the x stuff go? And I tell you guys, the x stuff is still right there. So if you just turn over u on the other side, you have this x squared minus 1. And if you just turn over this du on the other side, you have this 2x dx. It's kind of like a note card. So it's just hidden behind there because that's what they're equal to with respect to u. But now that you have your integral like this, it's one of your types. So we had this rule for powers of x's. The integral of x to the n dx is equal to x to the n, you add 1 to it, and divide by it, plus c. But it doesn't have to just be x. It can be any letter. If you put a u here and a u here, and then a u goes right there, that rule still holds. And so this is going to be equal to then u to the, you add 1, so 11 divided by 11, and then you add c. And then the idea is since you made that substitution, you want to go back to your x's. And so this is going to be equal to, just turn that u over on the other side, you have that x squared minus 1. So I have x squared minus 1 to the 11th divided by 11 plus c. And there's our answer. And if you want, you can check that answer by simply taking the derivative of this. When you take the derivative of that, you'll see you actually do get back this integrand up there because it is the antiderivative after all. So that's our first example of doing an integral by substitution. Before we think too much, let's do it again. So let's take a look at this one right here. So this is b, and we're going to do the integral of 5x squared e to the x cubed dx. And so I got to figure out what to make my u equal to. So u is going to equal what? And you'd like your u to be the thing on the inside again. So when I look at this, you have a couple choices. You have this 5x squared here, but that's not really on the inside. And then I also have this x cubed. So x cubed actually is on the inside, is the inside of the e function. It's e to the. So I'm going to let that be my u. I also like that to be my u because when you take a derivative of x cubed, you basically get an x squared back. You're off by a constant. So remember, the trick to doing this integration by substitution is really just look for a function and its derivative. So down here, when I look at this thing, I see a function right here, and this is basically its derivative. It's off by a constant, but we'll be able to take care of that. So now when I take the derivative here, du, and again, you can write if you want du dx, but I typically don't. I usually have to just move that dx, over to the other side. Let me get that off there. There we go. I usually move that dx over to the other side. So this is going to be equal to, so I take a derivative of this, and that's 3x squared. Then I put that dx over here. And now I'm looking for my substitution. So I see where I'm going to put my u. My u is going to go right here. But for my du, I have this 3x squared dx. And notice I don't have a 3, I have a 5 right here. So I'm going to have to take care of something. I'm going to have to make these kind of line up. So the way you do that is I just get rid of this 3 by dividing it out on both sides. So I'm going to divide both sides by 3, and that makes my du equal to, or du over 3, equal to x squared dx. And so what I can plug in for is I can plug in for this x squared dx right there. That'll be my du over 3. And so what is this going to be equal to? This is going to be equal to, I have the integral. The 5 has to stay, so the 5 stays right there. I have this e to the x cubed, so that's going to be e to the u, because x cubed is my u. And then this x squared dx, like I just said, that becomes my du divided by 3. So du divided by 3. So look at this again, because it's important that you see like the x stuff is still there. It's just on the other side. So the idea is if you turn over x cubed, there's a u there. So right behind u, you have an x cubed. And behind du over 3, you have a x squared dx, because that's what it's equal to. And so that's what we mean by a substitution. So hence the name integration by substitution. So make up a u, we find what du is, and then we substitute in, and it turns it into one of our types. So here I can rewrite this. I can pull out the 5 and the third. So I have 5/3 the integral of e to the u du, which this right here is one of my types. So remember, we have this rule, what's the integral of e to the x dx? You're just looking for its antiderivative, and that's just e to the x plus c. And that works for any letter. So if we just write a u here instead of an x, what we have basically is like another note card. You turn it over on the other side, you have e to the u plus c. So this will be equal to 5/3. Turn over that note card, and we have e to the u plus c on the other side. And so now this is going to be equal to, we're going to turn over the u to get the x stuff back, right? So the idea is you make it all about u, but then you go back to your x's in the end. So it's 5/3 e to the, and then remember u is x cubed, so you turn over and there's an x cubed hidden behind it, and then you have plus c. And that's our answer for that one. All right, so we have one last problem to do up here. So part C, so let's just move it over here a little bit. So let's take a look at this one. And so for C, what do I have? I have the integral of x divided by 1 plus x squared dx. And again, it's not one of my types. And so I'm going to have to do something to it to turn it into one of my types. And that's the big idea through the whole entire section here on techniques of integration. How do we turn it into one of our types of integrals that we know how to integrate? So what am I going to let my u be equal to? And so you can let u be either the top, or you can let it be the bottom. And it's up to you. If you let it be the top, it won't work. You could try it if you want. If you let it be the bottom, it's going to work out. So we're going to let our u be 1 plus x squared. And then our du, so just take a derivative of this thing right here. So what's the derivative? The derivative of 1 is 0 plus, and the derivative of x squared is 2x. So you just get a 2x. And then instead of writing that dx over here, because that's what we did, we just write on the other side to make the substitution look better. And so there's my dx. And so now how are we going to substitute back in? Well, I usually tell you guys, I like to pull this apart first, just so you can see what it actually is. So it's 1 divided by 1 plus x squared, and I can put that x on the outside. So then it's really clear, there's my u, and so this will be equal to the integral of 1 over u. And then that x dx, I don't quite have x dx. I got an extra 2 right there. So I just got to get rid of that 2 first. So I'll just divide both sides out by 2. And so du divided by 2 is that x dx. And so I'll replace this with du divided by 2. And remember, the x stuff is still there, all behind everything, but I can clean this up, and you see I get one of my types. So I'll pull out that 1/2 out in front, and I get the integral of 1 over u du. And so we have this as one of our types. You have the integral of 1 over x dx is equal to ln of absolute value of x plus c. And it's valid for any letter, so any variable, basically. So you just put a u there, and you can see what to do. And so this will be equal to 1/2. And then you turn this, basically note card over, and it's ln of absolute value of u plus c. And so substitution makes it about u. And so don't forget, you got to go back to your x's. So I'm going to replace my u with this 1 plus x squared up here. So I have 1/2 ln absolute value of 1 plus x squared plus c. And I can actually drop off these absolute values because the thing on the inside is always positive. So when you square a real number, you always get back a positive number or 0. But if you add 1 to it, it's always positive. So the absolute value of a positive number is always positive. So we'll rewrite this as 1/2 ln. And instead of absolute value, I'll just put parentheses 1 plus x squared and then plus c. And so there's our answer for that one. So these are all good little problems involving integration by substitution. So these are indefinite integrals. So what we're getting back here are actually anti-derivatives. The next question we want to look at is what happens when we work with definite integrals. And so here we want to use integration by substitution to find each definite integral, and then we'll use a calculator to draw a picture of the shaded region calculated. Right? This way, what I think is important is that you see that the number you get actually represents something, and so you can draw a picture to see that representation. All right, so let's look at this first one right here. So again, I'm going to copy it down. So the integral from -1 to 0 of 1 over 1 minus 2x dx. And I know it's a substitution because it's not one of my types. So it's not a power function. It doesn't have an EDX in it. It doesn't have a 1 over x. It doesn't fit the trig stuff. So I got to turn it somehow into one of my types. So my idea, since we only have one technique of integration, is to use that one technique. So I'll let u equal. And again, you only have 2 choices. You can let it be the top or the bottom. The top won't do anything for you. So it has to be the bottom. So we'll let it be 1 minus 2x. And then du will be equal to, so you just take a derivative of this side, so it's 0, and the derivative of -2x is just -2. Now I write the dx on the right. And so I see how to make my substitution here. I have 1 divided by, and this is my u right there, so I'll put a u. And then I'm left with this dx over here, and so I got to be careful because I have this -2 on there, so I'll divide out by -2 first. And so I get du divided by -2 is equal to my dx. And so now I can replace that dx with what it's equal to, that du divided by -2. And then don't forget, I have to change these limits of integration. So up to this point, everything's been the same as it was before. The only difference when you're doing these definite integrals and substitution is that now you have to change those limits of integration. And the reason for that is that this is actually x equals. And down here, you're going to wind up being with u equals. So we don't normally write the variable there, but it is implied. And so how do we figure out what u is? Well, we have a relationship right here relating u's and x's. So if you want to find u of 0, we're just going to plug it in right there. Or if you want to find u of -1, again, we're just going to plug it in for x right there. So let's start with u of -1. So what do we have? We have 1 minus, and then we have a 2, and then times a -1. which equals 1 minus, and then 2 times -1 is a -2, so +2, which equals 3. So the -1, when x is -1, u becomes +3. Versus when x is 0, u becomes, well, again, just plug it in, plug 0 in right there, and so you get 1 minus 2 times 0, which equals 1 minus 0, which is 1. So right here you have a 1. And so now we'll clean this up a little bit. We'll bring out the -1/2. So we get -1/2, the integral from 3 to 1 of 1 over u du. This is now one of my types, so I can integrate it. So it's going to be -1/2 ln of absolute value of u from 3 to 1. And then this is equal to, so remember how this works. The idea is you plug in 1, and then you subtract off when you plug into 3. So it's going to be -1/2, and you can actually pull that -1/2 out if you want to. ln of absolute value of 1 minus, so I always kind of say that's an evaluated at, but I think that's a minus sign. So minus, and then plug in 3. So ln of absolute value of 3. And so finally, I know ln of 1 is equal to 0. So that's a 0. And so I get -1/2 times negative ln of absolute value 3. So that's actually what? ln of 3. Drop off the absolute value if you want to. Let's move this over a little bit. And so I can drop off that absolute value because 3 is positive, and then divide it by 2. Let's make that look a little bit better. And so that's how you do integration by substitution with a definite integral. So notice it looks very similar to what we did before. So over here, it's the same steps basically. The only difference is now you have to change those limits of integration. And notice when I do the problems, I set them up the same way every single time. It's really important that you follow a certain sort of pattern when you solve these problems. That way it goes into your longer term memory. So we have one last thing to do on this problem. We're going to use a calculator to draw a picture of the shaded region calculated. So let's take a look at that because that's kind of interesting. So if you have a calculator, let's take this thing out here. And so we can graph this. So let me turn this on. And I can graph this function. So when you're working with your calculator, remember what you're actually graphing right here is the integrand. So we're to graph this right there. And so on my graphing calculator, I'm going to type in 1 divided by, and then in parentheses, left parentheses, 1 minus 2x. And then to get a nice looking window, I'm going to use my limits of integration. So that integral went from -1 to 0. So I'm going to put a -1 here, and I'm going to put a 0 there. And then I like to use a zoom fit button. So I go down here to zoom fit, which it just fits the output to the given input. So it gives me a nice looking window. So there's that function 1 minus, or 1 divided by 1 minus 2x. You can kind of trace it if you want to kind of see what's happening. So you can kind of see when the x values are negative, the y values are positive right there. So what I'll do is I'm going to come over here and just graph this. So basically, it's looking like this down here and coming up here between 0 and -1. You might ask how I know it hits right here. It actually hits at what, 1? Because when you plug 0 into this function over here, you get 1 over 1 out. And then to see the shaded region, I can use my calculator again, hit second trace to pull up the calculate menu, and then I can integrate this from -1 to 0. So lower limit's -1, upper limit is 0. It'll shade in that region right there. And I get what? Oh, I think I went the wrong way, guys. Oh, I have to change this picture a little bit. So let me change this. So this is above the x-axis. That's my bad. So let's change it. So here it hits 1, goes like this, basically. And there's -1, there's 0, and there's the shaded region right there. And you can see what it's equal to, because it's going to give us an approximation here. So should give us, ooh, Let me go back. So I hit the wrong number. So here, -1 to 0. I had to resume fit it. So hang in there with me. All right, second trace, number 7. Now here it's at -1 to 0. There we go. And it should give me a number. So what is the number? So 0.549. So we'll just write here about 0.55. So it's about 0.55. And the question is ln of 3 divided by ln of 2, that number basically, right? And this is an approximation right here. So that's approximately that area. And so let's just check it, see if it's right or not. And if it's right, you can move forward. If it's wrong, then we got to look at and see, what did we do wrong? So in parentheses divided by 2, hit enter, and it's solid. All right, so that checks. So I don't think it's right. I know it's right. Let's do one more of these, and then we'll be done with these types of problems. So let's do this last problem right here involving some trig stuff. So let me copy this down over here. So B, we're going to do the integral from 0 to 4 pi over 3 of sine of x and then cosine of x dx. So again, it's not one of your types. And so I'm like, well, it's probably a trig. It's integration by substitution. So what am I going to let my u equal? And here you have a couple of choices. You can let it be either sine of x or cosine of x. It actually doesn't matter. I'm going to let it be sine of x because it's on the left. And it doesn't matter because the derivative of sine of x is cosine of x. So in essence, I'm going to write a dx over there, I see the function and its derivative. So when you're working with an integral, these techniques of integration, we're going to have like 5 of them at the end of the day. When you see an integral and you're trying, it is not one of your types, you have to kind of look at it and judge which kind of technique you're going to use. And so what I usually tell you guys is if you see a function and its derivative inside the integral, then that's a key that tells you you're going to use this integration by substitution. And so then don't forget, I need to change these limits of integration. So what's u of 0? So you just plug in 0 for x right there. So that's sine of 0, which equals 0. And so remember, when you're evaluating trig functions, you just use that unit circle. So sine's the output and cosine's the input. So if you ask me 0, I can't stand, you can't see me, but I'm visualizing the unit circle. I'm like, oh, height 0, basically. That's the easiest way to do it for those types of points. But then if you ask me what the u of 4 pi over 3 is, so that's sine of 4 pi over 3. Now, that's a little bit trickier to do. So on the unit circle, I mean, I know where 4 pi over 3 is. So 4 pi over 3 is pi over 3 past pi, right? Because it's like 3 pi over 3 is pi, and you go one more pi over 3. So you're down there in the third quadrant. But I don't memorize what sine of pi over 3 is really. So there are tricks of the trade. So here, let me just kind of draw a picture for you. So whenever I do trig stuff, I always do all students take calculus. The A means all the trig functions in the sense of the sine, cosine, and tan are positive in that quadrant. Only the sine is positive in that quadrant. Only tan is positive in that quadrant. Only cosine is positive in that quadrant. And so if the angle is 4 pi over 3, I start here and I do pi over 3 4 times. So it's like 1, 2, 3, it's like 60 degrees. And then one more time. So that's 4 pi over 3. And so I see I'm in that third quadrant right there. So what that means is that the sine is negative. So I have negative sine of that reference angle. And so the reference angle is the angle, the smallest angle you make with the x-axis. So it's just negative sine of pi over 3. And now I do know the sine of pi over 3 because way back when I was taught this little table. So for these sort of standard reference angles, you have 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Those are in degrees, but I also know them in radians, right? So 0 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, and pi over 2 radians. And I know the sine of theta and the cosine of theta because I know how to count them out. And so I just have to remember one. And so the one that I know is I know the sine of 0 is 0, right? The sin gets you nowhere. So it's like, root 0. And then I just count up root 1, root 2, root 3, root 4, and these are all divided by 2's. And then for cosine of theta, it's exactly the same. It just goes the other way. So I can write root 4, root 3, root 2, root 1, root 0, and they're all divided by 2's. And so this table kind of lives in my head. So if you ask me for the sine of pi over 3, I got to remember pi over 3 is 60 degrees. And so over here, I can count it out in the table, and I get root 3 over 2. So that's actually equal to negative root 3 over 2. And so this will be equal to what? This will be equal to the integral. And so the 0 remains 0, so I have 0. The 4 pi over 3 became a negative root 3 over 2. And then this is my u, right? Sine of x is my u, so I have u. And then this leftover stuff, cosine of x dx, well, that was just my du. And so there's my substitution. I changed my limits of integration. And so now I can actually integrate it. So it's going to be equal to, and so how do you integrate u du? Well, it's just a power. There's a 1 here, so you add 1 to it. So I get squared divided by 2. And I evaluate it from 0 to negative root 3 over 2. And so now what do? I plug in the upper limit, and then I subtract off when I plug in the lower limit. And I'm going to kind of go slow here so you can see what I'm doing. So negative root 3 over 2, I'm going to square that and divide it by 2. And minus, now I'm going to plug in 0, so 0 squared divided by 2. And then the second term or last term is going to go away because it's just 0. I'm going to square out this thing right here. So negative is going to go away. Root 3 times root 3 is 3, and 2 times 2 is 4, and that's all divided by 2. To simplify this, 2 is like 2 over 1, so you multiply by the reciprocal. So it's 3 over 4 times 1/2, which equals 3 over 8. And so there's my answer. One thing that I like to point out is that you should notice when you do a definite integral, you never go back to your x's. So notice right here, when I integrated it, I never had to go back to my x's. It was just always about u. And over here, in this problem, after I integrated it, I never had to go back to my x's. It was always about u. Versus back over here, when we did all these problems, we did have to go back to our x's. Right? Because remember, in indefinite integrals, you're looking for antiderivatives. So the idea is for the antiderivative, it should be an x because your integrand is given to you in x's. But for definite integrals, you never go back to your x's. If you go back to your x's, I usually tell you guys you're making it harder than it needs to be. You never have to go back. It's the easiest way to do it. All right, so we're not quite done. We still need to draw the picture here. So let's pull up the calculator one last time. And let me turn it on and go to y equals. Let's clear this out and then type in that integrand. So as sine of x in parentheses and then cosine of x. And then I'll make my window go from 0 to, what was it, 4 pi over 3. So 4 pi divided by 3. And then I'll do a zoom and zoom fit. So I just change x min and x max, and then I let the calculator do all the work for me. And so it should give me a nice little graph here. And so I see the x-axis, which is kind of nice on this one. So it just goes up, goes down, goes back up, and comes back down a little bit. So I can copy that down over here. So I'll copy it down over here. So it kind of went up. Oops, I got to look and see where it started. So it starts at the down, up. Okay, so it starts here, down here, back up here. And then I think it went down just a little bit, so just a smidgen. So down just a little bit. If you want, you can put 1s on here, -1, but you don't have to. And then I'm going to see what the integral is. So I hit second trace. I'm going to go down to number 7, which is the definite integral. And I'm going to type in 0, enter, and then upper limit was 4 pi divided by 3, hit enter. And it found it. I will tell you that sometimes the calculator rounds funny from window to window. So if it goes to an error, I usually tell you guys maybe make your window a little bit bigger because it's rounding in a weird way in different windows. So here's my shaded region here, getting all this stuff right here, to right down there. So it was 3 pi over 4. So maybe I should put those limits on there. And then what number did I just get back? So let's take a look and see what number I had on there. So I had 0.375. So it was 0.375. And so we hope that 3/8 is that. I'm pretty sure it is, but we'll check it real fast. And so 3 divided by 8 is that number. So that 3/8 represents that shaded region, basically. Remember, it's not actually area because the integral will count this as positive, but it'll count the bottom part here as being negative. So it kind of subtracts that off to get that 0.375, but it checks. So I know it's correct. And that's it. So that's integration by substitution.